Hi everyone, this is our chapter 20 video, which is all about the specifics of hypothesis testing and confidence intervals. Now, a quick note on p-values, and I say quick note because we explored this a little bit in class, what a p-value is. But in short, a p-value is just a conditional probability. So if you remember the phrasing probability of A given B, that's exactly what this is. So in a hypothesis test, what we do is we assume that the null hypothesis is true. So given that the null hypothesis is true, a p-value tells us the probability of observing what we did in our sample, okay? So for example, if our hypothesis is that p is equal to 0.5, but our p hat value from our sample is 0.15, so 15%, that's a really significant difference, and that would likely lead us to believe that a p-value would be really, really low in that case. So that's why when that p-value is below our alpha, typically 0.05 or 5%, that's when we reject the null. So just remember, a p-value, it is a conditional probability given or assuming that our null hypothesis is true. Then a quick note on alpha levels, or that alpha value that we compare our p-value to. So remember that when the p-value is low or less than alpha, that's when we reject the null hypothesis. And just some terminology for you, if that p-value is low relative to our alpha, we call that result statistically significant, okay, meaning that there's something here, something important here. So just another recall for you, for confidence intervals, we found alpha by taking 1 minus that confidence level percentage, and that alpha level is exactly the same thing as what we compare our p-value to in a hypothesis test. So you can actually find a confidence interval that corresponds to that hypothesis test based on whatever your alpha level is, okay? So if your alpha level is 0.05 and you're doing like a one-tailed test, like greater than or less than, then you can find the corresponding confidence interval for that test. So hypothesis testing is great. They are very accurate, but they are not perfect, okay? Because we never compare our p-value to an alpha level of 0, because that would just be impossible. So we need to have some margin of error whenever we do a hypothesis test. So we're never 100% confident in our results. So when it comes to hypothesis tests, much of the time you are going to be correct. Your conclusion for rejecting or failing to reject the null will be accurate. But when that's not the case, there are two types of errors that we can make. The first one is when the null hypothesis is true, but we reject it. So if that null hypothesis is true, but we reject it, that's what we refer to as a type 1 error. And then when the null hypothesis is false, so it's not true, but we fail to reject it, that is called a type 2 error. Now on this next slide, I'm going to show you a table that is really useful in remembering what these errors mean. Anytime that I'm dealing with errors with a hypothesis test, I actually have to make this table, otherwise I goof up type 1 and type 2. So when it comes to the null hypothesis on our top there, you see that either the null can be true or the null can be false. There's no in between, either it's true or false. And then on our left side here, also our two conclusions we have are either we can reject the null or we can fail to reject the null. Well, when it comes to rejecting the null, when that null hypothesis is false, that is correct. We want to do that. If that's a false null hypothesis, we want to reject it. So that's good to go, no mistake there. Same thing could be said if the null is true and we fail to reject it, that's also a correct decision, because if it's true, we don't want to reject it. That is a good to go situation. Where the issues arise is when we have a null hypothesis that is true and we reject that null. That's what a type 1 error is. And then if we have a false null hypothesis and we fail to reject it, that is a type 2 error. Okay, so like I said, I've been doing this a little bit longer than you guys have, and I still have to make this table just so that I don't mix up what a type 1 error or a type 2 error is. A lot of the time on the AP exam and on my tests, I will not only ask you to do a hypothesis test, but I'll also ask you, in the context of this problem, what would a type 1 error look like, or what would a type 2 error look like? So a couple of things on making errors, or these type 1, type 2 errors. You might be wondering, how often will a type 1 error occur? And since that type 1 error is rejecting a true null hypothesis, the probability of a type 1 error is our alpha level. So typically that's going to be about 5%. And that's why we can actually modify that alpha level. 5% is kind of the standard, what we go to if it's not stated otherwise. So in general, you can say it's about a 5% chance. A test's ability to correctly reject a false null hypothesis is called the power. So if we have a false null hypothesis, then a test's ability to correctly reject that is called power. Now, power, I have to admit, is a very dense topic. We may or may not dig deeper into this in class, but what I really want you to know is type 1 error, the likelihood of that is our alpha level. And then when it comes to type 2 errors, that's again when the null is false and we fail to reject it. That's a type 2 error. And we assign the probability of that happening with the letter beta, or the variable beta. And the value depends on a parameter, so we don't actually know how to calculate that. And you don't need to know how to do that at all. So just know that beta is the probability of making a type 2 error. So I mentioned power a little bit earlier. Again, power is the probability to correctly reject a false null hypothesis. Again, if that null is not true, it is our ability or probability of correctly rejecting it. Okay. So all you need to know about power for now is that power is equal to 1 minus beta, because the beta level, that's the probability that a test fails to reject a false null hypothesis. So the complement of that would be 1 minus beta. So probability of making a type 1 error is alpha, which we actually know that's either 5% or whatever we assign our alpha to. But the probability of making a type 2 error is beta. And that is something that will have to be given to you. You will not have to calculate that yourself. So I'm not going to go too intensively into this idea of power, but on this next slide, I'm going to show you the relationship between alpha and beta. Again, that's the probability of making a type 1 error and the probability of making a type 2 error. And really you might be asking yourself, well, why don't we just make beta as small as possible? Why don't we make alpha as small as possible? And the fact is that you cannot do both at the same time. And you're going to see this visually here on the next slide. So what we have here is the relationship between making a type 1 error, that's on our top, and the relationship also with making a type 2 error. Okay, so on the top we have supposing that the null hypothesis is true, and then on the bottom, suppose the null hypothesis is not true. Well, what we see in red at the top, our alpha level, again, that is our probability of making a type 1 error. And if we look at the bottom, that red shaded region is beta, which is the probability of making a type 2 error. So as we can see, if we were to scoot that alpha level further to the right, in other words, make alpha smaller, then the opposite is going to happen to our beta. Beta is going to get bigger, and the probability of a type 2 error is going to be increasing. So that's where the idea of that alpha of 0.05 comes from. Some much smarter person than I am decided that 5% for alpha is kind of that nice middle ground of balancing the probability of type 1 error and the probability of a type 2 error. Okay, so just know that they are kind of inversely related. As one increases, the other one's going to decrease, and vice versa. And for this one, just know that in order to reduce a type 1 and type 2 error, well, for type 1, this is kind of immediate. You're going to pick a smaller alpha level. As we saw, that's going to increase your probability of a type 2 error. But for both of them, to decrease, the likelihood of type 1 and type 2 errors, you can always increase your sample size. So let's take a look at an example here. Treatment for skin cancer is extremely painful and very expensive. Luckily, tests for skin cancer are 99.7% accurate. Researchers use hypothesis testing to determine if a patient has cancer. So in our null hypothesis, we're going to assume you do not have cancer. And then our alternate is then that you do have cancer. So we're not even dealing with numbers here, okay? So a question I might ask you, for example, is number one, explain what a type 1 error is in this context. And also, what would a type 2 error look like, and which one is more detrimental? So maybe take a moment to pause, think about what a type 1 error would be, think about what a type 2 error would be, and then which one would be more detrimental. If you need to use that table, go ahead and do that. All right, so I'll remind you, a type 1 error, that is when the null hypothesis is true, but we reject the null. So in this case, that would mean you do not have cancer, but you are diagnosed with it, okay? So if we think about the consequences of this, you're gonna go through all these treatments, even though you don't need it. It's gonna cost you a lot of money. So there are definitely some issues and some consequences to a type 1 error in this situation. Now, a type 2 error, that's kind of the opposite of that. That's where the null hypothesis is not true, but we fail to reject it. In other words, you do have cancer, but you are not diagnosed with it, okay? So obviously, in this situation, you should be getting treatment and you're not getting it, so that could progress to a much more significant situation and could mean bad long-term effects as well. So which one is more detrimental in this case? Well, I think both are pretty awful. This one's kind of up in the air. But to me, type 2 error is probably a little bit worse, only because you're not getting the treatment that you should be, and that could potentially endanger your life. Obviously, you don't want to get some treatments if you don't need them, but at least you don't have cancer that could ultimately take your life. So this is a type of question you might see either on my tests or quizzes, homework assignments, and even on the AP exam. All right, another example here. You've decided to play the Powerball, which has a $400 billion jackpot tonight. You're pretty careful about your numbers, and you correctly identify your winning numbers 99.99% of the time. So that means once you look at your ticket, you correctly identify them 99.99% of the time. That doesn't mean you win that often, that just means you correctly identify them. So unfortunately, our null hypothesis, just because that's what our odds would probably say, is that you are not going to win the lottery, and our alternate hypothesis is that you won the lottery. So again, think about what a type 1 error is, a type 2 error, and then which one is more detrimental. All right, hopefully you pause to take a moment to think about that. So type 1 error in this case, that is where the null is true, but you reject it. In other words, you did not win the lottery, but you think that you did. So think about some consequences with that. First off, it'd be kind of embarrassing. Share with the world, hey, I won the lottery, and you haven't done that. Maybe you walk up to your boss and say, yep, I'm out of here, but you didn't actually win the lottery. So there are obviously some very difficult consequences to that with the type 1 error. Now with the type 2 error, this is where the null is not true, but you fail to reject it. So in this case, you actually won the lottery, but you don't think that you did. So maybe you throw that ticket away. You have no idea, but you won the lottery. You threw $400 billion away. So obvious consequences there. You're missing out on a lot of money. So which one is worse? I don't know. They're both pretty bad, but if I threw away $400 billion, I'd probably feel a lot worse than if I quit my job. So which one's more detrimental? Again, I'll leave that up to you. I'm going with type 2 error in this case. Another example here. So high school is done, and before you know it, you've graduated college. In pursuit of a job, you have a 3 p.m. interview at a great local corporation. You are good with scheduling. You are correct about appointment times 95% of the time. So our null hypothesis is that your interview really is at 3 p.m. And then our alternate hypothesis is that it's actually before 3 p.m. So the question here is the interview actually at 3 p.m. or is it actually before then? Okay. So again, think about type 1, type 2 error, and then which one is more detrimental. Okay. So type 1 error in this case, this is where the interview is at 3 p.m., but you think that it's before 3 p.m. In other words, the null is true, but we reject it. And if you think about this, really all this means is that you're going to be sitting in the parking lot early, and it might actually be a good thing for your boss to see, hey, this person is very urgent. They really want the job. They want to be here on time. So not a ton of negative consequences to that one. Maybe you had to take time off of school or work to get to the interview, but no big deal. Type 2 error, though, on the other hand, a little more detrimental. Your interview is before 3 p.m., but you believe it's at 3 p.m. So you think that the null is true, and you fail to reject that even though you should have. Your interview was before 3 p.m., should have been, but you believe is at 3 p.m. In other words, you're late for your interview, not going to give you a very good first impression. So again, I realize I've selected type 2 errors on the previous two, and this one I'm also saying type 2 is more detrimental. At this point, if you're feeling okay on type 1, type 2 errors, you can go ahead and stop watching, but I kind of think these are fun. So you've decided to build your own home in the middle of nowhere. This one is what I would like to see in a house that I could buy someday. It's probably never going to happen though. Okay, when it comes to building floors, you've decided on a material that you believe can hold 160 pounds per square foot, which is the necessary strength to hold people up as they walk on the floor. So our null hypothesis is that the wood can hold 160 pounds per square foot, and the alternate is that the wood can hold less than 160 pounds per square foot. So type 1 error, type 2 error, think about those and what one is more detrimental. Type 1 error in this case, that is where the null is true, but you reject it. So that means that the wood can hold that amount of weight, but you think that it holds less. So some consequences of this maybe are that you go to Home Depot or Lowe's and reinforce your floors even though you don't need to. So maybe you're out a little bit of money because you think that you need more material to make the floors hold that weight, okay? Now on the other hand, a type 2 error in this context, this is where we should have rejected the null, but we failed to reject it. So in other words, the wood cannot hold the weight, but you think it could hold it, okay? So this means we think that the floor is nice and safe, but really it's not. So that could lead to some pretty bad bodily harm, of course. People could fall through the floor, all that stuff. So for the fourth one in a row, I'm going to say type 2 error is more detrimental. All right, and the final one. Up to this point, the US, 85% of citizens have flown in a plane. Because of better accessibility to travel, it is believed that that rate has gone up. So this one, I'm actually using a more traditional hypothesis test format. As we can see, P is equal to 0.85 is our null, and we want to know, has P increased from 0.85? So type 1 error, again, that is where the null is true, so it is 85%, but we reject it. So what does that mean? The percent is actually still 85%, but we are making the claim that it has increased. Whereas a type 2 error, that is where the null is false, but we fail to reject it. In other words, we did not find evidence that P has gone up from 85%, but really it has gone up, okay? So this is a little more comparable to what you might see dealing with actual proportion hypothesis testing, but know that you can also apply these type 1, type 2 error concepts to non-numerical situations.